Every 2 years, during SOEST Open House, faculty, students, and staff share their research and love of science with students and the community. In this special episode of Voice of the Sea, we join Sea Grant Extension Agent Pelika Andrade, learning about her work studying ʻOpihi and the cultural practices that support productive ecosystems. Pelika, so this is your ʻAʻoaʻoina project.
It's part of our ʻAʻoaʻoina project, yeah.
Can you tell me what you're trying to show today?
Okay, so just ʻAʻoaʻoina is just broader, just trying to build communities of conscious watchers. We wanted to introduce our community, our kids, to the intertidal zone as one of the roughest places to be, right? But the coolest place to be because it's where most of our kids meet the ocean. We just brought some ʻOpihi because ʻOpihi, that's what we love here in Hawaii, right? And that's kind of what they're gonna see when they get to a rocky shoreline.
Are any of these shells from Oahu?
No. Yeah.
Do they get this big on, have you ever seen?
I'm sure they do, but if they do, I hope no one tells people where they are. Yeah, but most of these are collected out on the Big Island and Kauai, a couple from Kaho'olawe, and some in the northwestern Hawaiian Islands, up in Nihoa and stuff. We do a lot of research on the intertidal on other parts of our project in ʻAʻoaʻoina. We're looking at intertidal productivity of the ʻOpihi fishery. So we did a lot of gonad work to do GI for ʻOpihi and looking at spawning behavior and spawning capacity on different sizes. So no, we didn't raid. We did eat them, but we were looking at GI. So we have a lot of GI information over the years.
Tell me what the GI is. What's a gonad?
Okay, so gonads are the reproductive organs within our animals. So for ʻOpihi, there's male and female. Some of our researchers are finding hermaphrodites, so the ability to go both ways. And then what we look at is their reproductive capacity. So a GI is a gonad index.
Okay.
So we're picking ʻOpihi. If we pick below legal size, which is 1¼ inch ʻOpihi, we get a permit. We're looking at different size classes. So what we did was we picked 10 ʻOpihi within every species across size classes. We measured the length, the width, the height, weighed the whole animal, took the animal out, weighed the animal by itself, dissected out the gonad, weighed the gonad, and sexed the gonad. So the gonads look green if they're females and like a creamy yellowish if they're males. We divided the gonad weight by the total weight of the animal, and you get a percentage.
Okay.
And then we track that percentage over time, and you get like peaks and troughs. And the peak is when they're kind of gearing up to reproduce, and then when it drops again, they reproduce. So we know around what time of year they reproduce, and so there's a window. It's not like on January 5th they reproduce, right? It's like a window between these certain months that they're gearing up, and then they release, and then they drop again, and then they gear up and release. So we see a window in the fall and a window in the spring.
And are those times when it's important to not harvest the ʻOpihi as much and to leave them alone?
I'm a believer that there are important spawners and not important spawners, whether they're not spawning or spawning. Important spawners are those that have the most eggs. Whether they're spawning or not, which one is more important? The big guy.
The big one.
Yeah. So whether they have eggs or not, they're important. So if we not collect just because they're spawning, we wouldn't take both. And then if we went in when they're not spawning and collected them, we still are removing the most important spawners.
Right.
So for me, that it's a good practice, but it's not the best practice. So I'm not trying to say get stuff when they're spawning, but I think we need to relook at that rule, because whether they're spawning or not, they're still important or not.
Right.
And that's what fish do. We talk about eating these things and talking about traditional food sources. We are starting to take away the liliha, or the deliciousness and the richness of foods. And unfortunately, when they're spawning is when that deliciousness and fattiness happens. So basically what's happening is with that rule, when they're not spawning, we're taking important spawners. And we are taking them when they are not delicious.
Right.
So it's kind of trying to find a balance there. So what was the question?
Is it important to leave them alone while they're spawning?
I believe they're important to leave them alone when they're important spawners.
Right.
Not in the action of spawning, but when they are the most productive no matter what, spawning or not, leave them.
Does their productivity go down as they get bigger?
I think they hit a plateau. I do believe, and right now we have some colleagues that are doing like really, really great lab aquaculture kind of work that are getting it down. So Anthony Mao and Kim Morishige are doing like some really, really great histology work, and then we're gonna actually go into another round of histology paired with shell aging. ʻOpihi, we're finding from Anthony, has told us that if you, like a tree ring, if you cut the shell, you can actually tell not only how old they are, you can actually tell how fast they grow and in what seasons they'll grow. Because he was saying too, when they're getting fat with gonad, they actually will stop growing or slow their growth because their energy is going someplace else. He can confirm that you can actually tell age from the outside, so we don't have to take the shell and cut them. And by age, we can be able to tell like how much spawns they've actually released. And then from the histology, the bigger the ʻOpihi and the more mature the ʻOpihi, the better the quality of egg is. So we can give you a better idea of not only the capacity of spawning, but at what sizes and what ages they would give us the best quality egg. That's coming up over the next couple years.
And then
it's super exciting,
it's gonna come together with like the best tasting one.
And the best tasting one. So I'm encouraging eating really good tasting ʻOpihi. Our intent, a lot of Nakilo Aina's intent is how do we understand productivity so we can continually eat from our shoreline, because Costco gives us melted snow caps that's happening over there, right? To package and ship and all of this. We have this kind of like false security of if we leave this, it looks beautiful, but the alternative is to create a demand in really unhealthy practices, which is store-bought, huge agricultural systems that actually do a little bit more damage to our watershed. It's finding a balance and having a real conversation about what management, what conservation, what preservation, what pristine looks like in a global setting. And so that's what we're kind of looking at on a small scale.
So you talked a lot about the field science, the different kinds of lab science that are going to understanding the biology of the ʻOpihi and that might inform management. Are you looking at like historical, cultural practices of managing the species, and how does that relate to what you're finding in the science you're doing now?
Historically, we know they ate it. We know in more recent history, it's a super important for baby parties and all of that. When we talk about traditional knowledge, these are an item of a practice. I go back a little further to a system of practice. And the system for me is the ability for this to always be present. Cultural practice wasn't about us eating ʻOpihi. It was the ability for us to eat ʻOpihi over generations, right? So it's two different things. So our concern is, again, how do we understand the productivity so we can continue the traditional practice of allowing our future generations to have productive landscapes. And the cultural practice was not eating something, right? It wasn't ʻOpihi, it was productive systems. And then that's what our research is geared around. It's understanding productive systems and seeing if management is actually supporting productive systems. And we're finding it's really not. We're going on this new exploration we're calling PAC, so productivity and carrying capacity. And after 10 years of really looking at ʻOpihi populations over landscapes across the whole archipelago, we're finding that there's key components that make habitat productive or not. And not all black rock are productive habitats. So windward, leeward has a huge difference. So windward habitats are much more productive just because of the constant wave action and exposure to swell. And leeward, their exposure to swell, yes, but it's not as consistent. So the habitats that you see are much different on both sides of the islands. When you go to some shorelines and you only see sometimes 2 ʻOpihi, people go, oh my God, we over-harvested, and they like go into crisis mode, right? But sometimes that habitat can only support 2 ʻOpihi, and that's good. But we have to be able to recognize that. So our PAC, our productivity and carrying capacity project that we're heading into right now is to really start to look at wave action, the intensity of impact, how often waves actually the swell will hit, right? That's leeward, windward kind of thing. And then sunlight is a huge component. So we were seeing in places like Nihoa, on the north side of Nihoa, huge wave action, a lot of rough water, great habitat, like plenty rock, because it's this cliff, and no ʻopihi. And we're like, what's happening? And then we figured out that because of how people grow taro patches, on taro patches that are really up on the north side of mountains and cliffs, they'll actually leave those taro patches fallow because for 3 months out of the year, they don't get sunlight. And then we were like, oh, that's why. So for 3 or 4 months out of the year, these cliffs that are really, really tall and kind of a little bit leaning over, they don't get sunlight. So for part of the year, they're getting limu, but then they go dry for 4 months, so they can't support a population. So you're only going to find like 1 or 2 that are just hanging on there for the next influx of potential waves, but no limu. So Nihoa's has that. I'm a Napali on Kauai at Ho'olulu. There's this beautiful cliff crater that you don't find a lot of ʻopihi. I'm assuming other parts of that as well. We want to go to Molokai and kind of look at their northern facing cliffs to see like how productive it is, and it's natural to not have anything on it just because of sunlight. Fresh water, we're finding that there's a sweet spot of salinity that actually there's too much fresh water, not so good, too little. It still works, but not so good, and there's a sweet spot. So we're trying to find what that salinity looks like so we can be like, yeah, this is the place where you're gonna find plenty. And it's okay to harvest a little bit more.
The University of Hawaii Sea Grant College Program, helping coastal communities of Hawaii and the Pacific through research, education, and outreach. Serving the community, from elementary to graduate students. Hawaii Sea Grant.
We're looking at habitat and what that growth and shrinkage looks at throughout the year. And then we're counting densities and looking at what a habitat can carry. So when we rest areas in long-term rest, we look at something that looks kind of like this. And then if you leave it, right, you have plenty. And then if you leave it, does this look healthy to you? And a lot of people say, oh, there's plenty and it looks super healthy. But unfortunately, rocks don't grow habitat, right? They don't grow. So when you start getting too much, you reach a point of carrying capacity. So who's the first one that dies?
The big ones.
No. All of our little guys not only die, they don't settle because there's no place to settle. So we start getting a push out. So there's a settling that happens. We found recruits, like little dots. So what recruits look like is you can't even, unless you know what to look like for, you find the recruits. So we're finding that recruiting happens, but then they just get mowed over. So what happens is you're gonna start to see a habitat that is left to rest start to look like this. And then it'll start to slowly look like this. So if you rest it, this is what you'll find. And actually this is too much. So you start to get a habitat that looks like that. Yeah. So if you go to places like Mokumana, French Frigate Shoals, where you have a really stable habitat that doesn't grow and shrink, you just have the same carrying capacity. Your habitat doesn't grow, doesn't shrink, and because there's no huge wave change action because it's in the middle of the lagoon, you just have really big ʻopihi with no recruitment. And it's not because there's no seed, because we found a lot of recruits the last time we were up there, but they just can't compete. So you just have a lot of big ʻopihi and no recruits. And then you have some shorelines that actually have some small guys in there, but it's a pseudo recruit because when you have a calm, so you have a stable habitat, and then when you have a lot of storms come through, this habitat, you want visuals? So let's just say that this is your stable pink zone and stable habitat, and this is summer, yeah? And then the storms come through winter, and this habitat grows out. So you have an expanding habitat. And so you have a lot of recruits, so a lot of babies settle in. And you come in June, and you like are super, super happy because you come and count this. And these guys are still here. You come and count this, and you have all of this recruits happening, right? But then summer happens, and the waves stop. And then this starts to shrink. So all of these start to move down. And then this starts to shrink, and this starts to move down. Until all of them are like squished over here. And then they hit carrying capacity. So who dies now? Because this goes away.
The little ones.
So it's kind of like a pseudo recruit. So when we go in June and we count 20,000 ʻopihi that are all like this size or this size, we like feel real good about ourselves, warm fuzzies, and we're like, oh, they recruited, and there's plenty, and there's so much. Healthy shoreline. And then we go back in August, and we go back to this, and we see this, and then everyone goes, oh, people came in and over-harvested. Sometimes it's not the case. It just can't carry it. So there's this natural thing happening that upsets it. But then, so that's naturally. And then what happens is when people do over-harvest, so if they leave this alone, they can keep this down, right? Because this is the big limu, yeah? So this is big limu. They don't eat this, but they can keep it back. So they're grazing and they're just keeping it back so this doesn't get bigger and bigger. But let's just say these four are needed to keep this mode. When you take one away, now limu starts to encroach, right? And so they're just trying to keep this back. So when another harvester comes and takes one more, this starts to encroach even more. And then you take one more, and this starts to encroach until there's just one just kind of doing this, and then this goes over. So this guy is just trying to keep that down, and then you have this. Once this sets in, our assumptions, and this is what we're testing, is this is hard to get rid of again. And this is the danger of over-harvesting. Not that there's no seed in the water, and that there's no habitat to attach to. So I think that's what happened on Oahu. There's plenty of seed in the water, but because there's no habitat to attach to, we aren't able to bring that population. So on Oahu, you can put in a management and say absolutely no picking, and you won't bring back as quickly the populations because there's no habitat. But if we go in there, and this is the experiment, and you help to reset the habitat, and you go in and like on a really dry, the October, November months when it's drier and everything's dying back, and you go and help it along, put some ha'uke because they're competitors as well, but they're grazers, to help start to clean it, you open up more ground for seeding to happen. And then you can start to reset. But then you have to put in the rest to make sure that they can keep up. And then when you hit that nice carrying capacity and understand it, you can start to, if we have 4 here and you potentially take 1 out, 3 more will settle in. Yeah? And then the next year, these 3 are a little bit bigger, and you can possibly maybe take 1 of these, and then more will settle in.
Gotcha.
And then you can start, and that's productivity. And if we're right, we can still eat, but still have this really, really great production happening on our shoreline. So that's the ultimate goal. Are we trying to accomplish what we believe is pristine and healthy, which sometimes isn't? Or are we trying to accomplish a goal of productivity so we can get to a place where we are tending to our native ecosystems and tending to our ecosystems to be productive, to feed us as well as thrive?
We are looking for a few heroes, mentors, trailblazers, innovators, a passion to change lives, spark curiosity, open hearts, and awaken minds, help students answer the question, who am I? This could be your calling, but this is no job. It's the journey of a lifetime. Be a hero. Be a teacher.
Welcome back. We're at the 2019 SOEST Open House, checking out more exhibits. Nick, can you tell me a little bit about the work that you do?
Here at UH, I'm in the Ocean and Resource Engineering Department, specifically doing ocean resources. So I study wave energy, how we can use wave energy for things such as ocean exploration, ocean science, as well as for other purposes such as security and things of that sort. I work on a device that recharges offshore vehicles, things such as underwater drones, as well as I work on a project to use wave energy to desalinate water for emergency disaster relief. In order to understand how to do wave energy, you have to understand how waves work to start with. So
and that's why we have the tank?
This is why we have the tank. The cost of doing wave energy has just been too high for power grid purposes, at least in the US here. If we were to go and use it for non-power grid applications, you're still able to produce a lot that doesn't need to be for people who want to turn on their lights and have it work immediately. say you want to charge batteries, say you want to power something that doesn't need to be running constantly. And that's where it really has a huge benefit over wind and solar. In areas where maybe you don't have the best sunlight, you don't have as much power, and that's something that's especially limiting for people doing ocean science by the Arctic and by the Antarctic. This is where wave energy could really shine.
Can you talk me through some of the other things that maybe you're using the wave tank to teach today?
We're teaching a lot of the processes that happen near shore here. One of my favorite beaches to go to as a kid was Bellows. And so I'd go into the water at Bellows, and you know when you're walking in and all of a sudden it gets super deep and you're like, whoa. But then you see other people and it seems that it's only ankle deep a little bit further out. What's happening? Why is that? This wave tank is perfect for showing that, because as the waves come, they crash and they scrape sand away and they pile it up into a little sandbar, which you can kind of see right here.
Yep.
And so it happens multiple times. As you're walking out, it gets deep and then it shallows back out. And this is a perfect example for someone who just earlier today was like, oh, I'm going to Waimanalo. And I was like, this is what you're going to see. And they go there all the time and they just never understood why that happened. This, you can actually see it from the side. Additionally, we're showing things such as how ocean plastics end up on shore. You have your rubber ducky on the top here, and it moves closer to shore. But the other one is moving the exact opposite direction.
Oh, that's so cool.
So you can actually see the undertow happening right here. We've had some people actually from the civil engineering department come and ask us questions on like what happens when you have a structure. We'll take the paddle and we'll show when you put a wall in what happens with erosion.
Oh, can we do that?
Yeah. So imagine that this is your seawall, and we're going and we're putting it into the sand here. As the waves come, they'll go and crash up against it, and if your seawall isn't designed well, it will start to scrape away and scour. And so if you squat down, you can kind of see a little divot forming.
Yep.
And over time, this will scrape away. So it'll retain all the sand on one side, but not on the other. Mm-hmm. And now you've lost a lot of what was supporting this wall, and it'll fall over. So it's really cool. We have a couple of wave tanks like this, and part of our lab here, we look at different types of structures that, when you design them correctly, they don't cause these effects. And how can we make it so that we're engineering ocean structures to be better for our environment? When you have a confined area like this and rainwater coming in, it causes the pH to go down, and a lower pH actually dissolves sand. So the sand will start to become very mucky and a perfect breeding ground for bacteria. And so you get a lot of diseases like MRSA, staph infection, that develop in those sediments in that stagnant water. So it's really important to make sure that in any pool that you have your water moving back and forth. And it's really important to have ocean engineers working on these ocean projects. Growing up here, I've seen what a rip current is. I've seen what these waves do. I can kind of gauge what's going to happen. So when I'm going and designing something, a part of it is based off of equations, and a part of it is just intuition. And so intuitively, I can know that in any computer model of how something will work, that doesn't take into account algae grows on things, how the different beach profiles will be impacting things, how we have specific currents that you can take advantage of. So for my research, I'm taking advantage of an area where it's a pretty enclosed tidal area. I know it goes back and forth, so if my thing is drifting around, it's not going to drift off the sea. It's going to stay where it's going to be at. And that's a benefit of knowing, okay, I should probably put it over here, rather than someone who comes here and is like, well, I don't know what the beaches are like here, so I don't know what exactly are good places to put things in the water or test things out. And that's really helped me in my career, because I can spend less time trying to investigate different places and be like, I think I know this is a good place to go and test something, do a verification of it, and be like, yeah, okay. I didn't have to go through a whole searching process.
Follow us on social media at Voice of the Sea TV. Mahalo for watching Voice of the Sea.